Let's take a look at another example of how we can write models for linear, exponential, and quadratic functions. Decide which type of model corresponds most closely to the data and write a model. So remember, the very first thing we're going to do is we're going to decide which model it is. We do that by graphing the points. Sketch a graph and see, is it a linear, exponential, or quadratic model. So if I do that real quick, we had 0, 100, 1, 250, 2, 625, 3, 1560, and 4, 3900. Okay, again, those are coming off my x, and I just made this my x's and this is my y's. When I graph it, I get a model that looks like this. Again, I'm going to rule out linear. I'm thinking it's probably exponential, but it could be quadratic. We don't know if it's going to come back over here. So I've ruled out linear. Now I just need to decide if it's a quadratic or a exponential function. Remember, the way we do that is to see what its growth rate is. Okay, because again, we're looking between an exponential model, a times our growth rate to the x, or a quadratic model, y equals ax squared. Just two simple models there. So let's figure out how much this is growing each time. What do we do to 100 to get 250? You know, we're multiplying by 2.5. Do we multiply by 2.5 every single time? The way we figure that out is we divide. 250 divided by 100. That does equal 2.5. 100 times 2.5 equals 250. Let's see if that works here. Take 625 and divide it by 250. If you divide that in your calculator, you get 2.5. Take 1,560 and divide it by 625. In this case, we get 2.496. And then we can take 3,900 and divide it by 1,560, and we get 2.5. So notice this one right here is not exactly 2.5, but it's really close. Looking at this, this means that after every hour, we're increasing by 2.5. We're increasing 2.5 times. So from here, multiplying by 2.5, multiplying by 2.5, you can see the explosion of the exponential function. So if your growth rate here is pretty much the same, at least pretty close, we can say that this is an exponential function. It's an exponential function because this b here, this is important. This b represents either our growth or our decay rate. Our growth rate here is 2.5. We're multiplying by 2.5 every single time. So now all we have to do is figure out what a is. So take any one of these points. I'm going to use 0, 100. Remember, these are my x values and these are my y, and plug it into your equation here. For y, I'm going to say it's 100 equals a, that's what we're solving for, times b, well b is 2.5, raised to our x, well our x is 0. When I go to simplify this, remember, anything raised to the 0 power is just 1. Anything raised to the 0 power is 1. So we get that a equals 100. We have an a, we have a b, we have a model. So now we can write this as y equals 100 for a times our b, which is 2.5, raised to our x. That means I can plug in any one of these x values. So for example, if I plugged in 2, if I grabbed my calculator and said 100 times 2.5 raised to the second, I would get 625. If I tried it with 3, raising it to the third, I would get 1,562.5. Again, not exact, but really, really close. So we can say that this model represents this set of data. Again, when it asks you to write a model, first make the decision. Is it a linear, exponential, or quadratic model? If you can at least narrow it down to exponential and quadratic, figure out your growth rate. Figure out how much it's changing each time. In this case, we were multiplying by 2.5 every time. If your growth rate is the same, it's exponential. Once you figured out what that growth rate is and you've decided it's exponential, select an xy value to solve for a, your leading coefficient. Then you can plug all that information back into your model, and you have an exponential model that represents your data.